Welcome back, everybody. Today we're doing a deep dive into Proba-3.
Proba-3.
That's right.
Yeah.
We're going to be looking at some stuff from the ESA website, some articles about it.
Cool.
And this is really cool stuff. I mean, you're probably familiar with satellites, but this is like next level stuff.
Yeah.
We're talking about two satellites flying in formation, like so precise. It's like they're one giant instrument.
Yeah, it's really cool.
Yeah, and get this, they're going to create a virtual telescope bigger than a football field to unlock the secrets of the sun's corona.
It's incredible. You know, this is really where I think we start to see how space exploration is really pushing the boundaries of technology.
Right.
You know, and Proba-3 is kind of laying the groundwork for a lot of technologies that could change how we explore the cosmos.
Yeah.
You know, not just observe it, but actually get out there and do things.
I'm intrigued. Let's break this down.
Yeah.
So Proba-3, we're talking about two satellites, right, orbiting Earth in a highly elliptical path.
Right.
That on its own is pretty standard, right?
Yeah. That's pretty standard. Yeah. We've been doing that for a while.
Okay.
But the real innovation here is that they're designed to fly in a precise formation.
Okay.
You can almost imagine like two cars speeding down the highway, you know, perfectly aligned, just a hair's breadth apart.
Oh, wow.
That's the level of precision we're talking about.
That's an incredible feat. And this is a first for ESA.
Absolutely.
Wow.
Yeah, this is a technology demonstration.
Okay.
And it's being spearheaded by Senior Aerospatial
Okay.
and a consortium of European partners.
All right.
And yeah, if this works, it opens up all sorts of possibilities for future missions.
Okay, so we've got these two satellites in formation, but what's the point of this cosmic dance?
Well, there's two main goals.
Okay.
First, to prove that we can actually control multiple satellites with this level of precision.
Okay.
Because if we can imagine the types of large-scale instruments we could build in space, you know, think about...
So it's not just about showing off our space skills, but building towards something much bigger.
Exactly. And the second goal is scientific.
Okay.
This formation is going to create a giant virtual coronagraph to study the sun's corona.
Okay.
So think of it like this one satellite acts as a giant shield, blocking the blinding light from the sun,
Right.
allowing the other satellite to observe the fainter corona
Gotcha.
in unprecedented detail.
So it's like finally being able to see a rare bird hidden in the glare of the sun.
That's a great analogy.
Yeah.
And what's even cooler is that this will allow us to see the corona closer to the sun's surface than any previous mission.
Really?
Yeah.
Wow. Okay. So all of that sounds great in theory,
Yeah.
but I can only imagine that getting those satellites to move in such precise formation
Yeah.
can't be easy.
Oh, it's incredibly difficult.
What are some of the challenges?
Well, I mean, for one thing, it's not just about keeping them at a fixed distance.
Right.
They have to deal with, you know, the sun's heat causing expansion and contraction of materials.
Oh, wow.
You know, they're hurtling through space at thousands of kilometers per hour.
Right.
You can't just slam on the brakes.
Right.
And then testing this kind of formation on the ground is nearly impossible
Yeah.
because we can't simulate those distances or speeds accurately.
Right. So it sounds almost impossible.
It is a huge challenge.
So how do they actually plan to make it work?
Well, that's where the ingenuity comes in.
Yeah.
So they've developed a system of sensors and systems that all work together
Okay.
to maintain that precision.
Right.
And here's the kicker. The satellites need to be highly autonomous. They're like self-driving spacecraft, constantly monitoring their position and making adjustments to stay in formation
Really?
with minimal intervention from ground control.
Wow.
So think of it as a constant dance with the satellites making tiny, intricate steps to stay in sync.
So they're choreographing a ballet in space, essentially.
Exactly.
But what tells them where they are and what adjustments they need to make?
Okay, so it starts with what's called a metrology system. Metrology, yeah.
Right?
You know how we use GPS here on Earth to figure out our location?
Right.
Well, they have a similar system, but with several layers.
Okay.
So they use GPS, they use a coarse lateral sensor,
Okay.
and then the star of the show is the fine lateral and longitudinal sensor.
Lots of acronyms.
Yeah, we love our acronyms in the space business.
Okay, so FLLS.
FLLS.
What's so special about that one?
So FLLS is all about precision.
Okay.
This thing can measure distances with an accuracy of 300 micrometers.
300 micrometers.
To give you a sense of how tiny that is, it's thinner than a human hair.
Oh, wow. Okay, so these satellites know exactly where they are relative to each other.
Yes.
With incredible accuracy.
Yes.
But how do they talk to each other and make decisions?
So they use what's called an intersatellite link, or ISL.
ISO.
Yeah, think of it as a high-speed data connection between the two satellites.
Okay.
It allows them to constantly share data
Okay.
and coordinate their movements in real time. Without it, the whole formation would fall apart.
Okay, that makes sense. So the sensors provide the information, the ISL allows them to share that information, and then how do they actually move and adjust their positions? Do they have tiny little steering wheels or something?
Not quite steering wheels, but they do have thrusters.
Thrusters.
Yeah, tiny little engines
Okay.
that fire in short bursts to make extremely precise adjustments.
Wow.
It's like using a feather to steer a giant ship. Incredibly delicate, but incredibly effective.
That's pretty amazing.
Yeah.
But I have to admit, the thought of these satellites dancing in space, making these tiny adjustments with their thrusters,
Yeah.
it makes my head spin a little.
It's definitely mind-boggling to think about the level of sophistication involved.
Yeah.
And that's just the formation flying aspect.
Right.
We haven't even talked about the scientific instrument they're using to observe the sun's corona.
You're right. We haven't even touched on the virtual coronagraph and its implications for understanding the sun.
Right.
Let's dive into that next.
Absolutely. That's where things get even more interesting. Okay, so we've talked about how these two satellites will be doing their cosmic dance in perfect formation. But what makes that formation so useful for studying the sun?
Right.
That's where the virtual coronagraph comes in.
Okay, remind me, what exactly is a coronagraph and why do we need a virtual one?
So a coronagraph is essentially a tool that blocks out the sun's bright disk,
Right.
so we can observe the much fainter corona.
Okay.
It's like trying to see a firefly next to a spotlight.
Right.
You need to block the spotlight to see the firefly.
Gotcha. So how does Proba-3 achieve this? Do they have a giant sunshade or something?
That's where the virtual part comes in.
Okay.
Instead of a physical shade, they're using the two satellites to create the same effect.
Okay.
One satellite, the occulter, will precisely position itself in front of the sun, blocking its light from the other satellite, the coronagraph.
Okay.
This allows the coronagraph to observe the corona without being blinded by the sun's glare.
So it's like one satellite is holding up a hand to block the sun, while the other one takes a peek. Pretty clever.
Yeah, and because they can control the distance between the satellites with such incredible precision, they can create an artificial eclipse that's perfectly tailored to their scientific goals.
And what exactly are those goals? What are they hoping to learn by studying the corona?
Well, the sun's corona is this incredibly dynamic and mysterious region.
Yeah.
Temperatures reach millions of degrees, and it's where we see powerful events like solar flares
Right.
and coronal mass ejections.
Yeah, those are the ones that can disrupt satellites and even cause power outages here on Earth.
Absolutely.
Yeah.
So understanding the corona isn't just about satisfying scientific curiosity.
Right.
It's about protecting our technology and infrastructure.
Gotcha. So Proba-3's virtual coronagraph will allow scientists to observe the corona closer to the sun's surface than ever before, potentially giving us a much clearer picture of how these events occur.
Yeah, it's like having a front row seat to a cosmic fireworks show, but with the added benefit of understanding the science behind the explosions.
Okay, so what are some of the specific things they'll be looking for?
One of the key areas is understanding how the corona gets so hot.
Yeah, that's always baffled me. I mean, it's counterintuitive that the corona is millions of degrees hotter than the surface of the sun.
Right. It's like standing next to a campfire and feeling the heat increase the further away you get.
That is weird. What's the thinking on that?
Well, there's several theories, but it's still a bit of a mystery.
Okay.
Proba-3's observations will give us a much closer look at the processes that might be responsible for this unusual heating.
So they're hoping to solve one of the biggest mysteries in solar physics.
Indeed.
What else will they be investigating?
They'll also be studying the solar wind.
Ah, the solar wind. Isn't that what causes the beautiful aurora borealis, the northern lights?
Exactly. And understanding the solar wind is important for protecting our astronauts and satellites from its radiation. Proba-3 will be able to observe the solar wind very close to its source, helping us understand how it's generated and how it affects the space environment.
It's amazing to think how something happening millions of kilometers away can impact us here on Earth. What else will they be studying?
They'll also be looking at coronal holes.
Coronal holes.
These are cooler, darker regions on the sun's surface that are the source of high-speed solar wind streams.
Oh, okay. So they're like giant vents spewing out these streams of particles, which
Yeah.
can impact our magnetic field and cause geomagnetic storms.
Exactly.
Okay, so the more we know about these coronal holes, the better we can predict space weather.
Absolutely.
Hmm.
And finally, they'll be studying coronal loops, those giant arcing structures of plasma shaped by the sun's magnetic field.
Okay.
They can sometimes erupt, leading to those coronal mass ejections we talked about.
So by studying the corona in detail, Proba-3 is hoping to solve some fundamental mysteries about the sun
Yes.
and improve our ability to predict and protect ourselves from space weather.
That's the goal.
But I have to admit, this all sounds incredibly complex.
Yeah.
How do they even test something like this on the ground when you can't exactly recreate a star in a lab?
That's one of the biggest challenges of any space mission,
Right.
but particularly this one. They can't fully replicate the conditions of space here on Earth.
Right, those huge distances and speeds.
Yeah, so they rely heavily on computer simulations and modeling to validate their designs.
So they're essentially building a virtual twin of the mission in a computer to make sure everything works as expected.
Exactly. They model everything from the movement of the satellites and the functioning of their instruments to the behavior of the solar wind and the corona itself. It's like creating a virtual laboratory where they can test and refine their designs.
And I'm guessing they also do as much physical testing as possible.
Of course, they test individual components and subsystems as much as they can, but there are limits to how much they can do on the ground.
Sure.
That's why these missions require such a high level of expertise and meticulous planning.
Well, it sounds like the engineers and scientists behind Proba-3 are truly pushing the boundaries of what's possible. It's not just about the technology itself, it's about the new knowledge it can unlock.
Yeah.
So apart from potentially answering these big questions about the sun, what's the lasting impact of a mission like this?
That's what makes Proba-3 so exciting.
Yeah.
It's not just about achieving this one specific goal.
Right.
It's about developing technologies and techniques that could be used for all sorts of future missions.
Give me some examples. Where else could this technology be used?
Well, think about the possibilities of formation flying. It could be used to create giant space telescopes composed of multiple smaller satellites,
Okay.
allowing us to see further and with greater detail than ever before.
So instead of building a single massive telescope, we could have a fleet of smaller ones working together. That's a pretty radical idea.
It is, and it's not just limited to telescopes. Imagine using formation flying for Earth observation, creating a network of satellites that can monitor the environment, track weather patterns, or even assist with disaster relief.
That's incredible. It's like having a global network of eyes in the sky constantly watching over our planet. What other applications are there?
Well, think about the potential for space-based assembly and manufacturing. If we can control satellites with the precision demonstrated by Proba-3, we could use them to build and maintain large structures in space. Think space stations, solar power satellites, or even habitats for future deep space missions.
Okay, that image is mind-blowing. It's like taking that giant telescope idea and applying it to, well, everything.
It's a game changer for sure. And all of this is made possible by the incredible precision and autonomy of formation flying.
It's amazing to think that a mission focused on studying the sun could have such far-reaching implications for the future of space exploration. But before we get carried away with future possibilities, let's dive a little deeper into one of the most unique aspects of Proba-3, the rendezvous experiment you mentioned earlier.
Yes, the P3RVX.
Yeah.
That's where they're really pushing the limits of what's possible with autonomous rendezvous in space.
Okay.
It's like a mini mission within the larger mission. And it has some incredible implications for the future.
Okay, I'm all ears. Tell me more about this cosmic game of tag.
Okay, so imagine this. The two Proba-3 satellites are up there doing their formation flying thing, and then they decide to separate and play a game of cosmic hide-and-seek.
Okay, that sounds interesting and a bit nerve-wracking. Why would they do that?
So this is the P3RVX experiment, where one satellite becomes the target and the other has to find it, and rendezvous autonomously using just a camera and its onboard systems.
Wait, so they're not relying on GPS or commands from Earth?
Nope. The whole point is to test the feasibility of fully autonomous rendezvous in a tricky environment, like a highly elliptical orbit. It's a huge technological challenge.
I can imagine. What makes it so challenging? Is it like docking with the International Space Station only further away?
It's similar, but with added layers of complexity.
Okay.
First, they're dealing with a highly elliptical orbit, which means their relative speeds and distances are constantly changing.
Right.
Then they have very limited fuel for this experiment, so every maneuver has to be super efficient. And to top it off, They need to keep the Earth and Moon out of the camera's view during the rendezvous, which limits their movements even further.
Wow, it's like trying to thread a needle while riding a roller coaster blindfolded and with a fuel gauge that's constantly blinking red.
That's a pretty accurate description. But if they can pull it off, it'll be a huge step forward for autonomous rendezvous technology.
Okay, but why is this so important? How does this space age hide and seek benefit us back here on Earth?
Think about the future of space exploration and how we service and maintain our spacecraft. Right now, if something breaks on a satellite, we either have to accept it's gone or send astronauts on a risky and expensive repair mission.
So this rendezvous technology could pave the way for robotic repair crews, satellites that can fix other satellites.
Exactly. We could extend the lifespan of valuable assets in orbit and even reduce the amount of space junk by capturing and deorbiting defunct satellites.
That's a huge win for sustainability in space. What other possibilities does it open up?
In-space refueling is another big one. You imagine spacecraft that can be refueled in orbit, allowing them to stay operational for much longer periods. This opens up possibilities for more ambitious missions further into our solar system.
It's like having a cosmic gas station. You wouldn't need to pack enough fuel for the entire trip, which would make spacecraft lighter and more efficient.
Precisely. And if we think really big autonomous rendezvous will be essential for assembling and maintaining large complex structures in space, future space stations, lunar outposts, even Martian colonies, they could all be built piece by piece using this technology.
It's incredible to think how far we've come in space exploration and how missions like Proba-3 are pushing us even further. But let's step back for a moment and appreciate the engineering brilliance that makes all of this possible. What are some of the challenges the engineers faced when designing Proba-3?
Well, this mission is truly a marvel of engineering.
Yeah.
They had to overcome numerous obstacles to create a system this precise and sophisticated. Just think about the stability needed. You have two satellites that need to move with incredible precision, essentially becoming a single instrument spread across hundreds of meters.
Right, it's like building a giant telescope that's constantly in motion.
Exactly. So they had to minimize vibrations and thermal distortions that could throw off the formation.
Oh.
They used advanced materials and construction techniques to make the spacecraft both lightweight and incredibly rigid, all while withstanding the harsh environment of space.
I bet computer simulations played a big role in designing something that complex.
Absolutely. They modeled everything: the thermal expansion of materials, vibrations from the thrusters, even the impact of micrometeoroids, to ensure the spacecraft could handle whatever space throws at them.
It sounds incredibly challenging. How do they test these systems on the ground?
They use a combination of techniques. They tested individual components as much as possible, and for the larger system, they relied on sophisticated simulations that mimicked the conditions of space. They even have specialized facilities that can approximate some aspects of the space environment, though nothing can fully replicate it.
So there's always an element of the unknown when you launch something into space.
Absolutely. But that's part of what makes space exploration so thrilling.
Yeah.
It's about pushing the boundaries of our knowledge and capabilities and accepting that there will always be challenges to overcome.
Well, it sounds like the engineers who worked on Proba-3 have done an incredible job. They've created a mission that's not only pushing the boundaries of science, but also inspiring us with its technological ingenuity.
It's a true testament to human creativity and our desire to explore the universe. Proba-3 is a reminder that the future of space exploration is bright and is being built on the foundation of these amazing missions.
I couldn't agree more. Proba-3 shows us that space exploration is not just about sending rockets and probes into the void. It's about expanding our knowledge, pushing technological limits, and inspiring future generations to dream big.
And who knows what those future generations will achieve? Perhaps inspired by missions like Proba-3, they'll build those giant space telescopes, those self-sustaining spacecraft, and those outposts on other worlds.
It's exciting to imagine the possibilities. Well, on that note of cosmic wonder, we've reached the end of our deep dive into Proba-3. Thank you for joining us on this journey of discovery.
It's been a pleasure sharing these insights with you. Hopefully you've gained a new appreciation for this incredible mission and the brilliant minds behind it.
And remember, keep looking up at the stars, keep asking questions, and never stop exploring the universe around us. Until next time, this is The Deep Dive, signing off.